So what we've got on this picture here is just an example of how much energy humans use. So each person in the US uses 10,000 watts. Now that's a power, that's a rate of energy usage. And if you think that a large light bulb has 100 watts, you can see that everybody in the US has essentially 100 of those big light bulbs working for them all the time, day in, day out. And if you take the energy that we're using across the globe for everybody in the world, it's something like 15 trillion watts. So how do we create that energy? Well, you have power stations. The biggest nuclear reactor in the world in Japan is 13 billion watts, if you're running out of all these zeros. And then the Three Gorges hydroelectric dam in China is about the same or even larger, 18 billion watts. But you can see by that red writing near the top, we need 1,000 of those huge power stations to power what we need to keep going. So what about energy in the atmosphere? Well, there's lots of different sorts of energy in the atmosphere. So one sort is kinetic energy. That means like the energy of motion. And typically, say in a hurricane, the amount of energy that's used in a hurricane is about 530 of those huge, the largest power plants running for one day, just to keep that going. Now, where's all this energy coming from? Well, of course, it's coming from the sun. And this is what I'm interested in. And this picture of the sun here is actually a fantastic picture taken from the SOHO satellite showing the sun at ultraviolet wavelengths. But just to show how active it is. Now, the amount of energy or power absorbed by the Earth, this is just what's absorbed by the Earth, this isn't the power being emitted by the sun, this is just what's absorbed by the Earth, is something like 100,000 trillion watts. So I was going on about how large the amounts of energy in the atmosphere are and how large the power requirements of human activities are. But here we are, look at this sun, it's giving us a hugest amount of energy into the Earth. So this is showing on very, very long time scales that the sun, how the sun affects the climate. So on the top left there, we've got pictures of the Earth's orbit around the sun. And you can see that the orbit is not a circle, it's an ellipse. That means that it's like an oval. And so that it's the orbit, it means that the Earth's going further and closer to the sun as it goes round the orbit in a year. And the shape of that ellipse changes with time on very, very long time scales. So it changes on time scales of 100,000 years. And if you look at the graph in the bottom left down there, what that's showing is temperature record extracted from an ice core, a Russian ice core sample, and it's showing how every 100,000 years there's a sort of spike in temperature. And it's thought that those spikes are due to changes in the ellipticity, so how elliptical the orbit is of the Earth going round the sun, can affect the climate. On the right-hand side, we've got shown how the radiation coming into the Earth changes through the air and across the globe. So what this is showing is up-down axis is going from the North Pole down to the South Pole, so across the globe, up and down the globe, and the right-left axis is showing time through the year. So where those red spots are is showing more radiation coming into high latitudes in the summer, and black showing no radiation coming into high latitudes in the summer. And rather obviously, it's colder in winter than it is in summer, and that's an effect of the seasons. And the orbits also change in terms of the tilt of the axis, of the Earth's axis towards the sun, and that will influence how those blue and red patches on the graph on the right affect the climate. So there are very obvious changes in climate due to those orbital and geometric type factors, but those aren't changes in the sun per se. They're not changes in the sun itself, they're changes in the sort of geometry of the Earth's orbit around the sun. So does the sun vary in other ways? And and the answer is yes. And this picture you've got up on the screen now, the blue one, is showing solar flares emitted by the sun. And these are big solar storms that come out on a timescale of minutes to hours, huge amounts of energy there, and you can't usually see them. And you can only see them in this picture because there's been a big disk. That big blue circle is a big disk that's been put between the satellite and the sun. The big blue circle is covering up the sun so you can actually see the flares. And those of you that can see the movie, good, so you can see it playing, you can see big puffs of white plasma energy. These are particles coming out of the sun. And they're solar storms. And when those bits of plasma and energy come towards the Earth, they can influence satellite communications and have an effect on power transmission and that sort of thing. So they're affecting not so much the climate as how we use satellites and things. So they're very important in themselves, but they're showing that the sun actually does vary. It's not sitting there as an inanimate object. Now what we've got, we can see two black squares in the middle there, but those correspond to the movies on either side of the screen. And the one on the left is a picture of the sun's surface, and it's showing the magnetic field on the sun's surface. And you can see those amazing little loops. And that's like if you have a bar magnet and you put the iron filings, they go in a loop around the magnetic field. That's exactly what is being shown there, with the magnetic fields on the sun's surface spouting in and coming out again. And you can see it's really active. And on the right, we have just one or two sunspots on the Earth's surface, and all those little granules on the Earth's surface. So this is an amazing picture of the sun's surface, again taken from a satellite, showing how active it is on those very localized and short time scales. No, what's causing the so hypernova flare says that solar radiation is causing the ice to melt in the Arctic. It's not the solar radiation that's causing the ice to melt. It's the greenhouse gases, like the carbon dioxide, warming the atmosphere, and that warming is causing the ice to melt, not the sun. There's an interesting knock-on effect with the ice and the sun, because if the carbon dioxide, if the greenhouse gases melt the ice, then there's less ice there, and then less of the solar radiation is reflected back to space. That means more of it gets into the Earth, which means that the Earth gets warmer than it would have done had it not been warmed up in the first place by the carbon dioxide. So that's quite a worrying issue. Amy's asking, is public opinion changing in the UK and the US? I mean, I think in both countries there's a small minority of people who are very keen, who believe that the warming is not due to carbon dioxide. And I think that runt of the public is the same probably in both countries, although perhaps the Tea Party movement in the United States has adopted that belief rather more strongly than the equivalent conservative groups in the UK. But I think as scientists what we have to do is explain the science, explain the uncertainties in the science, but also explain exactly what we do understand. And we do understand fairly clearly that recent global warming is due to greenhouse gases coming mainly from burning of coal and oil.